Welcome to The Explainer. I am so pumped you're here because today we are decoding the intense, high-stakes purpose of a medium-voltage circuit breaker on a marine electrical grid. Imagine standing in the heart of a massive vessel, right? You're surrounded by thrumming generators and thousands of amps of electrical current. In that kind of extreme environment, the medium-voltage breaker is your ultimate gatekeeper. We're going to break down the exact math used to size these critical components, and then we'll shrink down to the microscopic level to witness the violent physics of an electrical arc being extinguished. It's a fascinating journey into survival engineering, so let's get right into it.
Okay, let's dive into this. A medium voltage breaker really just has one brutally simple job, but it lives completely between two absolute extremes. First, look at the scenario on the left. This is its daily, kind of boring job. Switching on the full load current of the ship without even blinking. Day in and day out, it's handling the massive power needed for propulsion, thrusters, and hotel loads. But then, look at the second scenario. That is the terrifying extreme. When a catastrophic short circuit hits, that exact same breaker has to instantly, on command, switch off the absolute worst-case fault the network can possibly throw at it. It literally cannot fail, it can't weld shut, and it definitely cannot hesitate. Because if it gets this wrong, well, nothing downstream survives.
So, how do we actually know our breaker can survive that worst-case scenario? Well, sizing starts with a really crucial metric called the expected short-time withstand current, or IK for short. Take a look at the formula we've got here. IK equals the sum of each connected source's short-circuit power, which we call S, K, divided by the square root of 3 times the nominal busbar voltage, UN. What does all that mean in plain English? Basically, every single generator, large motor, and transformer connected to that busbar contributes to this total sum. You literally have to account for every single piece of equipment that can feed power into a fault just to figure out the massive wave of current your breaker has to withstand.
Now, what's really interesting about this slide is how we actually calculate that individual contribution, SK, for each source. You find it by taking the apparent power of the machine, SN, which is just the total electrical power it's built to handle, and you divide it by something called subtransient reactance, represented by XD double prime. Think of subtransient reactance as the machine's immediate electrical resistance to sudden changes. And here is the secret to understanding this formula. Lower reactance machines actually dump way more fault current onto the bus. So if a generator has a really low subtransient reactance, it is going to unleash a massive, instantaneous spike of power the exact millisecond a short circuit occurs. That violently high number, that is exactly what your breaker needs to be tough enough to survive. And that brings us to a pretty terrifying reality about marine power plants. We're talking about the sheer scale of the danger here. The fault contribution stacks with every single source you connect to the busbar. It's entirely cumulative. And here's the detail that catches a lot of people off guard. It absolutely does not matter if that generator or motor is just idling or barely carrying any load when the fault happens. If its breaker is closed and it's electrically connected to the bus, its full short-circuit power contribution gets dumped straight into the fault. The grid basically acts like a giant funnel, directing all that potential energy right into the short circuit in literally milliseconds.
Let's ground this in a real-world example so you can actually visually anchor how aggressively this fault power stacks up. Here we have identical generators, each rated for 10 megavolt amperes with a subtransient reactance of 0.15. Watch the running total of our withstand current, IK. With just one generator, the fault current is highly manageable, right? But add a second, and it doubles. Add a third, a fourth, and you can see the total IK absolutely rocketing upward. Every single time you parallel another machine onto that main switchboard to gain some redundancy or extra power, you are simultaneously raising the total short-circuit violence that the network can produce.
All right, I want to throw a scenario directly to you to make sure we're tracking this, because it's a super critical concept. Imagine you're down in the engine room. You've got 4 generators already running on your busbar, but the ship needs more power, so you parallel and add a 5th 10 MVA generator to the board. Think about what we just talked about. Does the required breaker IK rating for the switchboard go up, does it go down, or does it stay exactly the same? I'll give you a second to lock in your answer. The answer is up. More sources on the bus always equals a higher required IK rating. So the absolutely crucial point here is that adding a single generator isn't just about plugging in more power. When you add that 5th machine, every single existing breaker on that switchboard, even the ones installed years ago, needs to be aggressively rechecked against this new higher fault level. If the new cumulative fault current exceeds what your older breakers were designed to survive, a short circuit is going to blow them apart instead of safely interrupting the flow.
So you now hold the two equations that size every medium voltage breaker on a marine switchboard. This right here is your sizing toolkit. Just by understanding skill, you get exactly why engineers are so obsessive about fault calculations. You know for a fact that fault contribution is fiercely cumulative across every connected source, not just the ones running at max capacity when the fault hits. You have the mathematical foundation of survival. But how does the breaker actually execute that survival in the real world?
Let's move to and see how this builds as we get into arc extinction theory and the actual physics of the strike.
So imagine the contacts flying apart. The current doesn't just politely stop flowing. Oh no, it rips through the air, ionizing gases and creating a superheated plasma arc that bridges the gap between those separating metal contacts. To kill this arc, the breaker has to do 3 things in a fraction of a second. First, it stretches the arc, literally pulling it apart physically to increase its resistance. Second, it cools the arc, usually using insulating gases like SF6 or a vacuum chamber to strip away its thermal energy. But here's the crazy part. The arc doesn't actually die from stretching or cooling alone. It dies at step 3, precisely at the alternating current's natural zero crossing. 0, that is the magic number. Because marine grids use alternating current, the electrical waveform naturally drops to 0 volts and 0 amps 50 or 60 times every single second as it reverses direction. At that exact microsecond, at the current zero crossing, the arc naturally extinguishes itself just because there's momentarily no energy feeding it. And here is the ultimate climax of our whole explainer. Every single medium voltage breaker technology on Earth, whether it uses vacuum bottles, SF6 gas, or air chutes, exists for one singular purpose. It is designed to rapidly flush the space between the contacts with insulation so that when that natural zero crossing happens, the kill is made permanent. It stops the arc from restriking when the voltage waveform rises again just a millisecond later.
We've covered the relentless math of cumulative fault currents, and we've explored the violent, split-second physics of permanently killing a superheated plasma arc right at the zero crossing. Honestly, the breaker really is the unsung hero of the ship's electrical grid. So I'm going to leave you with this provocative thought to take back to your own projects. As ship grids expand and power demands keep growing, will your existing breakers actually survive the next generator you add? Understanding the formulas and the physics we explored today is really the only way to know for sure. Thank you so much for joining me on this explainer. Keep your curiosity sparked, and I will catch you next time.